Computational modeling of liquid crystalline properties. I'm going to present some review on this topic, semi-empirical calculations. Using semi-empirical calculation for the estimation of liquid crystalline properties, the most important method is the molecular interaction. The molecular forces are divided into two categories: short-range force and long-range. Former are frequently called valence or chemical force, are significant when molecules come close enough so that their electron cloud have possibility to considerable overlap. Contribution of short-range forces to intermolecular potential varies exponentially. The separation are independent on the specific nature of the interaction being considered. On the other hand, long-range interaction varies as r to the power minus n at large value of r, where n is a positive integer. Thus, the long-range energy interaction between two molecules varies as r to the power minus 1 to r to the power. Classification of molecular force. It is classified into basic two groups, long and short. Long range is again divided into electrostatic, which is additive, inductive, which is non-additive, dispersion, which is again nearly additive, but both are repulsive. Then resonance energy is attractive but non-additive. And short range is type overlap, which is attractive but not additive. Electrostatic energy. The electrostatic energy of is the interaction energy of the permanent charge distribution. However, the separation between molecules is large as compared to their dimension. The multiple expansion of various components like charge dipole, dipole etc. may be conveniently implied. Electrostatic energy is given by the expression again over here. Polarization energy or induction energy arises from the polarization of one molecule by the charges of permanent electric movement of the other. These interactions are relatively smaller. The electrical expression for induction is given by this, where B and P prime are the polarizability of interacting molecules. P and R represents the dipole moment, molecular separation, and tau is function of quadratic quadrupole moment. Dispersive energy. The dispersive energy is a consequence of quantum mechanical nature of electron. This may be explained on the basis of average interaction on an instantaneous electrical movement on a molecule brought about by fluctuation in electrical charge distribution, and the moment introduced by it on the interacting molecule. At distances that are large in comparison with the size of the interacting system, the dispersive energy varies as the inverse of sixth power of distance. However, the dispersive forces are always attractive for molecule ground state because of the inverse sixth power dependence. These forces vanishes very rapidly with increasing distances and are usually significant between nearest neighboring molecule only. London presented a sound description of dispersive forces on the basis of the second-order quantum mechanical perturbation theory and developed useful expression for their appropriate evaluation. Resonance energy. The resonance energy is the additional energy that result when the degeneracy is removed by interaction. The degeneracy may arises because one of the interacting molecule is itself in degenerate state, as is the case of hydrogen atom in excited state interacting with an ion or a polar molecule. However, during any particular collision process, the resonance energy may be either attractive or repulsive depending upon the quantum number describing the state of pair. Resonance energy has an important role in determining width of the rotational line in the pure rotation and rotation vibrational spectra of smaller gaseous molecules. Finally, magnetic interaction also exist with the molecule and they play a finite though minor role. These interactions are so big as compared to the corresponding electrical interaction that one can frequently ignore. Theory of long-range intermolecular interaction. This is often known as Rayleigh-Schrödinger perturbation theory, has been examined by a number of authors over a number of years. Here we present a theory according to Buckingham. The induction energy is therefore the sum of two parts. Induction energy is equal to e to the power a induction and e to the power b induction, where e to the power a induction e, which gives us dispersion energy summation of some function given here. Semi-empirical potential. Different form of intermolecular potential functions have been listed in literature. These have been used to calculate various properties. In choosing any particular form of potential function, one has to consider two factors: degree of realism desired and the numerical difficulties associated with the manipulation of function. Here the first function shows the rigid sphere and second is the point center of the repulsion. Square wave potential is represented in this figure. Southern model is also represented here, which is a modified square wave potential. Then comes the Lennardian potential, which is further modified by the Buckingham. The expression for well-known Lennardian potential is Vr is equal to 4 epsilon sigma by r to the power 12 minus sigma by r to the power 6, which is also known as 612 potential. The computational scheme for intermolecular interaction. A detailed computation have been provided by Cleveridge suitable for evaluation of interaction energy of large interacting system with whatever complexity. The simplified formula described by Curry as follows. Total intermolecular interaction energy between any two molecules may be expressed as sum of various contributing terms accordingly. E total is equal to E electrical plus E induction plus E dispersion plus E repulsion. The real E dispersion and represent the electrostatic, induction, dispersion and repulsion components respectively. Electrostatic energy. The molecular charge distribution is expressed as the set of atomic charge Q referred to as monopoles and the atomic dipoles M, which can be obtained by using any all-valence molecular orbital method. According to multi-centered multipole expansion method, the electrostatic energy may be expressed as the sum of individual terms between atomic multipole as under EL electrostatic is equal to EQQ plus EQM plus EMM plus so on, where EQM and EMM etc. are the monopole, dipole terms respectively. In general, the first three terms have been found to be adequate for the most of the molecular system. Polarization energy. The polarization energy, sometimes called as the induction energy of a molecule, is obtained as sum of induced polarization for various bonds involved. E induction for a molecule is equal to C minus 1 by 2 summation over U rho epsilon sigma is equal to dispersive and short range repulsion energy. These two terms have been traditionally considered together, as has been done in semi-empirical derivation of the Leonard or the Buckingham type cases. As mentioned earlier, Pitofsky adopted six exponential potential and later on modified the parameter to suit all type of molecular system, and which is given by the expression. Computation of interaction energy at various configuration. Here first shows the six phases of the molecule, and for interaction they are termed as stacking side A, side B, plane side A, plane side B, or in plane interaction side A, side B, and terminal interaction side A, side B, which is explored like this. This is the stacking example of stacking interaction. Then this is the when the molecules are interacted along a y-axis, then it is in plane interaction. When the molecule is interacted along x-axis, it is termed as terminal interaction. Here are some calculations showing the intermolecular interaction in liquid crystal with the same formula. E total is equal to electrostatic plus E polarization plus dispersion plus repulsion. This is the case of biphenyl 4-carboxylic acid, and here are the energy values for stacking interaction, and one can see the dispersion energy has major contribution to the total energy in the stacking. Similar is the case for the in plane interaction, planar interaction, and even in the terminal interaction. Another example is PN propoxybenzoic acid. Here we can again see the major energy comes from the dispersion, and the repulsion has also its own contribution, which reflect in the total energy. The characterization of mesogen, the following aspects were found to be useful. First, the pair potential in mesogens generally possess orientational specificity toward 0 or 180-degree intermolecular orientation. The relative value of interaction energy in state, planar, and terminal complexes are also very important, since if these values are comparable, it is more likely that the molecule will directly go into solid form from the liquid state. If any two of the above mentioned energy are comparable and possess tendency of sheet formation, cinematogenic character is more probable. Even of odd effect in homologous series roll up an isotropic pair potential. For the even odd effect, the role of terminal substitution, that is alkyl chain, has significant. All nematic crystal molecules contain at least one terminal alkyl chain. Plot of alkyl chain length versus liquid crystal phase transition temperature for two triple system is shown here. This is for the cyano system, that is 4 trans 4 N alkyl cyclohexane benzonitride, and this N represents the number of alkyl chain, and this is the phase transition temperature, and one can see that as number increases it goes into even and odd direction simultaneously. Another example is 4 and alkyl 4 cyanobiphenyl. Here again, as the N increases, initially the transition temperature decreases, but when it crosses the N is equal to 5, it shows the alteration in the phase transition up to the 9, and from 9 it becomes phase transition temperature become. This alteration in the phase transition temperature is an even odd effect in homologous series. The normal alteration of transition temperature can be explained by odd carbon atom alkyl chain having the terminal CH3, which extend the long molecular axis, whereas in the even number of carbon chain, the terminal CH3 tends to lie off the axis. One can see from here that when it is 3, it is in the same axis, but the moment it becomes 4, it goes off the axis. The homologous series containing R, OR, COR, where R is an alkyl, as terminal group of the following irregularity become apparent. The terminal CH3 in alkyl chain with an odd number of carbon chain atom lies along the long molecular axis. The homologous series containing R, OR, and COR as the terminal group, the following irregularity become apparent. The transition temperature of pneumatics decreases with increasing transition temperature of pneumatic decreases with a fairly distinct alteration. The amplitude of alteration also being reduced with increasing the chain length. If the first member of homologous series are already relatively long, the alteration is less apparent. Schematics are rarer with short chain but become more common with longer chain. The plot of transition temperature of schematics and their transition point to the pneumatic usually reaches a maximum to moderate chain length and decreases gradually with further elongation of chain. The plot normally shows no distinct even odd effect for schematics. An attempt has been made to correlate this energy with transition temperature, hence to understand the even odd effect at molecular level. The molecular chosen is the PN alkoxybenzoic acid, where the one side of this has polar group, hydroxyl polar group OH, and another side is alkyl chain, and the side defined as side A, side B for stacking, CD for in-plane terminal, E and F for the terminal. Stacking interaction. Stacking interaction is divided into two parts, part side A and side B. For this studies were out of two molecules, one molecule is kept fixed. Another molecule is allowed to move and rotate or orient itself. So when another molecule is have a interaction in next direction for one side of phase, then it is side A. And when it is in the another side of the molecular system, a transition along jet direction, then it is side B. And lowest energy configuration energy is plotted. Figures below reveal that dominant component of total energy is the dispersive energy. The contribution of polarization energy and electrostatic energy is negligible. Since stacking side A covers all the components, the benzene ring and the carboxyl group and alkoxy group and total binding energy is almost constant with the homologous number, which suggests that there is no role of long alkyl chain in stacking interaction of side A. Therefore, no odd even effect has been observed as evidence from this figure. But that is not the case for the side B. In the stacking interaction of side B, the role of alkyl chain is well distinct. As the chain is elongated from 2 to 3 and 4 to 5, the intermolecular separation increases. Since the odd alkyl terminal lies off the molecular axis, the extension of alkyl chain from 1 to 2, 3 to 4, and 5 to 6 increases one bond parallel to the molecular axis. So, in such case, interaction energy decreases due to increase the number of atoms at same intermolecular separation, and one can see the pronounced odd even effect in the side chain. Now, in plane terminal, that is side C interaction, it is clear that from this figure that repulsion energy show a slight alteration with homologous series. But the dispersive energy saw a compensatory effect. If the dispersion energy has major contribution to total energy, the total energy does not show the alteration with the homologous series. An interaction inside B. Again, we see that electrostatic interaction has some alteration, but the dispersive energy also having the compensatory effect of the electrostatic part, as the total energy does not show the any or even effect or alteration in the energy. In terminal, inside a E interaction, the presence of carbonyl group at one end show the tendency of forming dimer with double hydrogen bonding. It is also evidence from figure that interaction energy is almost constant with homolog number. Here the major contribution of total energy comes from electrostatic energy. This shows that the molecules have a strong tendency to form dimer by hydrogen bond. In terminal side F interaction between alkyl chain in the molecule have the band structure. The terminal interaction decreases with increase in the homologous number from 3 and onward. A minor alteration of energy between homolog number 1 to 3 is due to less pronounced band structure. Here also the major contribution in total energy comes from dispersion energy, while the repulsion energy show compensatory effect. When we come to the Total energy. The total stacking interaction side plus side with homologous number shows distinct or even effect. As a result, total interaction energy also shows the same effect. The amplitude of alteration in interaction energy decreases with increase in homolog number. The total number reported here corresponds to the association energy with the first neighbor of all atoms. This refers only to a local ordering energy. Quantum mechanical calculation. The problem with semi-empirical method is that it can only provide the rough estimation of other properties such as polarizability, dielectric constant, and other properties of liquid. Calculation based on quantum mechanical method or density functional theory can provide estimation of liquid. Right? A brief review of such calculation are there. There are two most important DFT method, hybrid DFT method. One is V3 leap, another is M062X. Here are the comparison between these. The B3 leap approach belongs to the hybrid approximation for the exchange hybrid correlation function. It is hybrid functional with for 15% artifact exchange. It, it is good performer for geometry optimization. M062X functional is based on the meta-GGA approximation because this includes all terms that depend on the kinetic energy, density, and are all based on the flexible functional form parameterization on the high-quality benchmark database. It is global hybrid functional with 54% artifact exchange. It is good performer for the main group thermochemistry, kinetics, and non-covalent interaction. The three parameters defining which relief have been taken without modification from Becke's original fitting of the analog B3P W91 functional to a set of atomization energy, ionization potential, proton affinity, and total atomic energy. Actually, in this method, fitting parameter obtained from the ab initio calculation. M062X belongs to M06 class functional, which relies on the spin density, cities, spin density gradient, and spin kinetic energy density. And for the non-local hybrid functional, artifact exchange M062X is a hybrid meta-functional, has excellent performance for the main group chemistry. It is quite accurate for the predicting the valence and the Rydberg electronic excitation energy, including dispersion, correlation, correction, provided the excellent result for the aromatic stacking interaction. General M06 family is constructed with the empirical fitting of other parameters.